Thank you very much for the introduction, and thank you very much to the organizers for giving me the opportunity to speak here. It's my first time ever in India, so it's an incredibly exciting time for me. And today I want to talk about non-abelian Hodge correspondence for stacks. So let's start with the basic ingredients. We're gonna set X to be a projective variety, smooth projective variety. Over the complex numbers. And let's fix G a reductive group. So non-abelian Hodge correspondence is about 3 moduli spaces. And let me introduce them as moduli stacks. So the first one is the Dolbeault stack. That I'm going to denote curly MD, or maybe curly L dol. It parameterizes semi-stable G Higgs bundles. E theta on X with vanishing rational Chern classes. So that's my first stack. So let me recall what's a Higgs bundle. So we're gonna take a G bundle E, and theta, the Higgs field is gonna be a section of the adjoint bundle of E tensor with omega 1 of X. And it should satisfy that theta is 0. So that's what a Higgs bundle is. Higgs bundles with some stability condition we're gonna consider. They form a nice stack, and it says here stack, the word stack reminds us that a Higgs bundle may have an automorphism group. So I am including this as part of the data of the moduli problem. Now here's another moduli problem. The RAM stack, curly MDR, it parameterizes G bundles on X with a flat connection. And again, I consider it as a stack. And the third main character of today is the Betty stack. That parameterizes representations of the fundamental group of X in G. So representations of pi 1 X in G. So we can see this as mapping stack from the classifying stack of pi 1 X to the classifying stack of G. And so these 3 stacks can be approximated by schemes in what's called good moduli spaces. So they have each of these stacks, there's some automorphism groups that are present, but there's like a way to get rid of them. And while M Dolbo is a stack, there's a scheme, upright M Dolbo, that sort of is universal for maps from this stack to any other scheme. So locally, this good moduli space map looks like a quotient of an affine scheme by a group, GLN. Let's take mapping to the spectrum of the invariants. So locally on the stack, this moduli space is given by spectrum of the invariant. So it's a GAT quotient. And there's also a good moduli space for the de Rham stack and the Betty stack. And they are all schemes, and they are quasi-projective varieties. And now the start point is this classical theorem due to many people, due to Kitchin, Donaldson, Simpson, who's here, and Corlett, and other people. So this is called like non-abelian Hodge correspondence. Is that the good moduli spaces of these stacks are homeomorphic. So there exists a homeomorphism between M Dolbo and M de Rham. And there exists a complex analytic isomorphism between M de Rham and M Betty. Right? So this is like a spectacular theorem that tells us that these three very different moduli spaces are actually homeomorphic. It does not tell us that they are isomorphic and algebraic varieties, and in fact, they are not. And that makes the whole story even more interesting. Yeah. Yeah, so the good moduli space of each of these stacks, the points are in bijection with polystable points of the stack. MDR? I think no, like just G bundles with flat connection. Yeah, semi-stability, yeah. But not polystability, right? Yeah, there's strictly semi-stable objects or semi-stable objects in this stack that are not polystable. All right, so the question for today is, what about the stacks? Curly, Dolbo, de Rham, and Betty. Are they, so the first question you may ask, are they homeomorphic in some meaningful sense? And my feeling is that they're probably not homeomorphic, but we can still ask the question cohomologically. So this is what I'm going to address today. So even if we are not able to say whether these stacks are homeomorphic, we'll be able to talk about the cohomology of these stacks, several versions thereof, and establish isomorphisms. Yes. They are not GLN gerbs. There's a more complicated. It's a more complicated GIT quotient than a gerb. Yeah. Yes for Dolbeau stack. No for de Rham or Betti stack. I did not write semi-stable. In Dolbeau, yeah, semi-stable is here. Semi-stable, yeah. So there's a stability condition here, but we don't need a stability condition for these other two. Yeah, any other questions? Yeah. So I'm not familiar with the higher Teichmüller space. I guess maybe maybe Oscar can answer this better than me. Like this is not a compact Lie group. This is a complex Lie group. So I don't know if that's what makes the difference. Yeah, but I don't know. I'm not familiar with this. So maybe Oscar can like say something. Yeah. Okay. Okay. Thanks for that. All right, so let me talk about previous work. So we are not the first people to talk, to like consider this non-abelian Hodge theory for the moduli stacks, not the moduli spaces. The first one to consider this was Davison. So previous work is this theorem in genus 1 due to Davison, and higher genus due to Davison together with Hennecker and Schlegel-Mejia. And this theorem says that if X is a curve and G is GLN, then there's an isomorphism between the Borel-Moore homology of these three stacks. So these three stacks, if we consider their Borel-Moore homology, which is homology theory, then the three are identified. They are isomorphic. And so this is what was known before our work. And I want to say a few words about how the proof proceeds. So this proof is really beautiful, and it uses a lot of deep results. So the proof idea is to first express the Borel-Moore homology of each of these stacks in terms of intersection cohomology of several auxiliary moduli spaces. So we express, the idea is express Borel-Moore homology for each of these stacks in terms of intersection cohomology of the corresponding moduli stacks for now a product of GLNs. And this procedure is a really deep thing. So this is very deep. It uses a lot of machinery, uses what's so-called integrality theorem. BPS cohomology. And some other things. And once you have a way of expressing this Borel-Moore homology, which is an infinite dimensional space in terms of this intersection cohomology, now we can use the classical non-abelian Hodge correspondence, because intersection cohomology, a nice cohomology theory for singular spaces, but it's homeomorphism invariant. So to conclude by intersection cohomology being invariant under homeomorphism, and classical non-abelian Hodge correspondence. Yeah, so it's the n1 and 2 have to add up to n. Yeah, we have to consider all those. And also let me say that it uses crucially whole algebras. So whole algebras is something that's only available as an algebra for structural group GLN. So generalization to other groups is hard because of this. So this needs GLN. And then this BPS cohomology really requires X to be a curve. So basically, it's really, really hard to generalize this method of proof beyond the GLN case and beyond the curve case. Yeah? This is the moduli space. Yeah. Yeah. All right, so now let me talk about, so basically the main thing that's needed is that these moduli spaces are symplectic. The moduli stacks are symplectic, so that really requires X to be a curve. Does that use more beyond the geometry of moduli spaces? In some sense, not that much more. There's like, these stacks are locally like Nakajima queer varieties. That's something that's used. It's very close to being symplectic and parametrizing objects in an abelian category. So maybe not, yeah, I'm not sure what else to say, but a lot of the techniques generalize to more general situations. So it's not that specific of an idea. But for us, it is because it requires X curve and the group to be GLN. Yeah. Not quite, actually. So here we're already in the semi-stable locus. So this comes more from, yeah, this comes from this whole algebra structure. So there's no theta stratification going on. There's no Harder-Narasimhan stratification going on for this. Yeah, it's not. I guess you have to like consider Jordan-Hölder filtration somehow. Like it's the way I see it, it's more or less like considering the good moduli space map. Yeah. Yeah, so the way this appears is because there's a direct sum map. So there's a direct sum map, but there's also like a roof where you consider like extensions, and there's like a roof like this, and this whole algebra like sort of maps the cohomology of this guy to the cohomology of this guy, and inside the cohomology of this guy there's this piece, so you map this into that, and sort of this generates everything up. Yeah. Fixed points. This, I think no, but maybe could be wrong. So they appear, yes, okay. So you can see them as like components of mapping stacks from BGM. So in this sense, it's like similar to fixed points for GM actions. R is just a number. Yeah, the number of copies of. No, like we're just considering all the ways of expressing n as a sum of some numbers. Always, yeah, all possible ways. Yeah, so there's many of these, so we can have to consider all of these. Yeah, thank you for clarifying that. Yeah, so we're considering in terms of these guys for all possible partitions. Yeah, thank you very much. So there's many of these. Yeah. Okay, so let me present a theorem. This theorem is joined with De Cataldo, Fernandez Herrero, Henecard, and Quinjo, so I wrote their names there. This is the first set of authors. So now we're going to take X, any projective, smooth projective variety, and G, any reductive group connected. Then there are isomorphisms. Canonical isomorphisms. As follows. So first we can consider the cohomology of these stacks. And they are canonically isomorphic, all of them. But, so this is usual cohomology. But, okay, Davison and company, they were doing Borel-Moore homology, but we can also do Borel-Moore homology. So also the Borel-Moore homology of these stacks are canonically isomorphic. And these stacks are singular, so they have interesting intersection cohomology. And actually, also their intersection cohomology is canonically isomorphic. Not only that, but the isomorphism between Dolbeault and de Rham, in these three cases, it preserves mixed Hodge structures. All right, and okay, that's not the end of the theorem. There's, let me continue. So continued. We can consider the universal cohomology theory, and that's motives. And if we talk about motives of stacks, then we find that the motive of the Dolbeault stack and the motive of the Dolbeault of the de Rham stack are canonically isomorphic. So these are rational et al. Wygotsky motifs. Okay, so think about it as just like the most general possible cohomology theory. So for that, these are isomorphic. There's also like a Borel-Moore version of these motifs. And the Borel-Moore version of these motifs computes the Chow groups. So that's a theorem, recent theorem of Bai and Park, that these Borel-Moore motifs know about the Chow groups of the stack and can recover the rational Chow groups in the sense of crash. So actually these two stacks, they have canonically isomorphic Chow groups. Rational Chow groups. All right, so this is what I want to talk about in the rest of the time. Questions about the statement? The first one is just singular cohomology. Yeah. Actually, I don't know. I think no. So this is a different thing. So sorry. Yeah, so this is a more flexible theory that naive motives. So I'm not saying that the class in the Grothendieck group of varieties is the same. These motives are constructing using a sheaf theory, like a universal sheaf theory. You're considering like the most possible sheaves on stack you can possibly consider and consider cohomology for those sheaves. So it's not the same as the class in the Grothendieck group of varieties. Yeah. But for instance, this theorem implies the theorem for cohomology and for Borel-Moore homology. So there's a realization functor that realizes motives into cohomology. Yeah, so that cannot be, yeah, they cannot be isomorphic because we know that these guys have like pure, so these guys have, in the case of curves, they have pure Borel-Moore homology, but this one is not pure because it's affine good moduli space. And that's the origin of the P equals W conjecture I'll talk about. So there's no way this can be true for the Betty stack. All right, so I told you this proof of Ben Davison, Henekar, Schenkel-Mejia was quite complicated and like very deep. So you would expect this to be even more complicated, deeper. But the good news is that it's actually pretty simple. So the proof of this theorem is in some sense a formal consequence of some things that were known for a long time. But it's a simple proof, so I wanna explain it. So let me sketch the proof. Okay, so the proof has two main ingredients. One is local triviality. I'm gonna say what this means. Of the Hodge moduli stack. And two is a compactification argument. Okay, let me rename this A and B. Okay, so step by step. The first thing to consider is what happens between the RAM stack and the Betty stack. So actually, the RAM stack and the Betty stack are complex analytic isomorphic. So there's the Riemann-Hilbert correspondence already provides a complex analytic isomorphism. So this implies that they have the same homology and Borel-Moore homology, because these are topological invariants. Okay, and this is pretty canonical. This is Riemann-Hilbert. So, okay, so one side of the correspondence, we're basically done. But now, so this was known, of course. And now what happens with the Dolbeault stack and the DeRam stack? Well, these two stacks can be compared using moduli of T connections. So this is another moduli problem that interpolates between these two stacks. So this is the Hodge moduli stack parameterizing T connections. This is a moduli stack over A1 with a few nice structures and properties. So first there's a GM action that makes the map to A1 GM equivariant. And if we look at the fiber at 0, that's going to be the Dolbeault stack. And if we look at the fiber at 1, that's going to be the DeRam stack. And if we restrict this GM action to the Dolbeault stack, we recover the GM action that scales the Higgs field. So the usual GM action. Okay, now, I said that the first main ingredient is local triviality, and this is a result proved by Simpson. And if we look at the Hodge moduli stack mapping into A1, this is not going to be a trivial family. So it's not going to be isomorphic to just the fiber at 0 times A1, projecting into A1. However, these two stacks have common étal neighborhoods. So this is the isotriviality result of Simpson that's really important. So it tells us that eta locally, this looks like a product. So eta locally on the source. Okay, so this already like makes you believe like homology is just gonna be the same. This splitting does not respect the GM action, of course. Okay, and yeah, so projection to A1. Yeah, thanks. Now, by this isotriviality is already enough to check that if I look at the constant constructible sheaf with value Q on M Hodge, or the push forward along F of the dual, or word of the intersection cohomology complex. For each of these different versions, it's enough to check that these are constant. So constant sheaf on A1 means it's pulled back from something that lives on the point. And isotriviality is important here because isotriviality guarantees that even though this map is not proper, base change still holds. So if I look at these complexes of sheaves, and I restrict to 0 fiber or 1 fiber, I'm going to recover the cohomology of of Dolbeau or de Rham stack. Sorry? Yeah. Sorry, what is, you're asking, what is this Hodge moduli? Yeah, so, exactly. So, okay, so, in the case of, let's say, curves and GLN, so I want a connection to be like a map from the bundle to the bundle tensor omega 1. And a connection should satisfy the Leibniz rule. So if I have a function G and a section E, this is going to be G times lambda S plus dG times S. So this is what the Leibniz rule for a connection is. And T connection means I'm going to put a T here, parameter T, right? And so when T is 0, this becomes a Higgs field because this equation means is linear, and I can act so this T is going to be the element that lives here on A1, and I can use the GM action to scale this lambda T, and everything is equivariant. So when T is 0, this will just be scaling the Higgs field. That's the action. All right. So the next ingredient is the following lemma. What numbers should I write? Forgot. 5, thanks. So the following lemma. So suppose that we have a map from Y into A1. Okay, let's suppose that there's a GM action acting everywhere, and let F be some complex of sheaves. So on Y. So this is going to be the derived category of inconstructible sheaves. And suppose that F is isotrivial. So is G isotrivial. So what does this mean? This means that I have this map from Y to A1, and this map itself is going to be locally a product. So locally, like R times A1. So there's smooth, let's say smooth maps A and B. And here, this is the projection to A1. Here, there's the projection to the fiber R. And what I want is that once I restrict this F to U, it comes from something that lived on R. So this is there should be an isomorphism between this and a pullback, something that lives in R. So projection to R, pullback of something that lives on this derived carrier of constructible sheaves on R. Okay, so I'm assuming that I have a morphism that is locally a product, but I have a sheaf that's also locally a product. And A and B are like smooth surjective maps. Yeah. And so the conclusion is if Y is DM, the Lyman-4 stack, and proper, and G is proper, then G push forward of F is constant. So this is isomorphic to pullback from something that lives on the point. Okay, so this is like a lemma, okay, that is not a hard lemma. It's something that we can use by checking that the unipotent vanishing cycles of this F is 0. So that's step 5. And now step 6 is that if we go back to our situation, and let's just for concreteness specialize to the case of cohomology. So we are looking at the push forward of this constant sheaf. If we take curly F to be the push forward to the good moduli space of this constant sheaf on the Hodge moduli stack, this is gonna live in, this is gonna be a sheaf on the good moduli space of the Hodge stack. Then this F is locally isotrivial for the morphism, the induced morphism G from the good moduli space of the Hodge stack to A1. So this is a consequence of Simpson's isotriviality result. All right. And now we have a locally isotrivial sheaf, and we just want to push it forward, but we cannot use the lemma because this map is not proper. So now the issue is that G is not proper, but we are going to solve this issue by compactifying. So the issue is that G is not proper, but there exists a compactification so this M Hodge lives inside M Hodge var, something that is proper over A1. So there exists a compactification, and this one is proper. And so this was known. So this was known by Simpson. And then many other people sort of extended this construction. And so what we checked is that F extends to a sheaf F bar in this compactification. So we have that J pullback is F, and here there's a boundary, right? So the boundary of this compactification is, so this may help you think about this compactification, is going to be A1 times Dolbeault moduli space minus the nilpotent cone. And now we're going to quotient by the scaling GM action on everything diagonally. So if we call this I, this I upper streak of this F compactified is isotrivial. For G, for the boundary map. And also F bar itself is isotrivial. And now we can use excision. So we can express this F, the cohomology of this sheaf, as an extension of cohomologies of this sheaf and this sheaf on A1. And then by the lemma, those are constant. And so this one has also needs to be constant. So 8 by excision, we have open and closed complements. Implies that G push forward F is constant, excision plus the lemma. Because for the boundary and the compactification, we have local isotriviality and properness. Okay, so that's basically the proof. Right, so the Dolbeault moduli space, so this is the compactification of the Dolbeault, no, wait. So this is not the compactification of Dolbeault. Wait, but so this is the boundary of this compactification. So yeah, you can think that over its fiber, every fiber is going to have the same boundary. That is Dolbeault minus nilpotent cone modulo GM. So the boundaries are like, they're all the same for every fiber. Yeah. you want to? Right, but it's really important to use the Dolbeault thing to compactify connections, because what's crucial here is properness of these fixed points of the GM action in Dolbeault. That's ultimately what guarantees the properness. So I don't know if there's a way to like compactify connections using connections, but we can compactify connections using Dolbeault. So it's like Dolbeault is compactified using itself, and the RAM is compactified using Dolbeault. Yeah. Okay. Any other question? F is a complex. Yeah, sorry, I might have said sheaf. So this is, sorry? Extensional sheaf. Yeah, sorry. Complex maybe, yeah. Yeah, thanks. Yeah, so as you can see, like this proof is very formal. So this is why it works. So basically this proof works for any sheaf theory. This is why it works for motifs as well. So it works, so this works. for any six-functor formalism satisfying A1 invariants and excision, for which motives are the initial one. So this is why it works for motives. Basically, the proof is so formal that it works in the most general possible scenario. So this construction of F bar really uses the specific compactification. Yeah. So I'm not sure, I guess no. Okay, so let me talk about some consequences. So P equals W conjecture after De Cataldo, Hausel, Migliorini, we're gonna generalize it for any G in some sense. So for this, we need to assume that X is a curve, but G is any. And so we're gonna take M Dolbeau mapping to its good moduli space. And then we can consider the Hitching fibration, which is proper. And we can call pi this good moduli space. So the perverse filtration, the ith piece of the perverse filtration of Borel-Moore homology of N Dolbeau is we're gonna look at the push forward of this dualizing sheaf for pi after pushing it forward to the Hitching base, and we're gonna take perverse truncation. And this guy here is pure mixed Hodge module. So if we take the cohomology of this guy, this is actually, all these filtrations are gonna split, and therefore we get a well-defined filtration PI. So that this is called the perverse filtration, uses perverse truncation and the Hitching fibration. And on the other hand, for the Betty stack, there's the weight filtration coming from Hodge theory. And the conjecture is that under the non-abelian Hodge correspondence for Borel-Moore homology, this perverse filtration agrees with the weight filtration on the Betty side. So this conjecture in the case of GLN and coprime degree and rank was proven by several people recently. And so now we can formulate the conjecture for any G. So under the non-abelian Hodge isomorphism. All right, and now finally I wanna use the last 5 minutes to talk about some other conjectures related to this. So these are analog of the Hausel-Thaddeus conjecture for any G. So now we're gonna still fix a curve, G, X, sorry. And we're gonna look at Dolbeau moduli stack for G. and also the Dolbeault moduli stack for the Lang-Lang's dual group. And it's very tempting to say these two should have the same Borel-Moore homology. And that will be an analog of the Hausel-Thaddeus conjecture in the case of GLN, sorry, in the case of SLN and PGLN. But it cannot hold, it's just not true. But it can be fixed if we take the loop stack. So if we take the loop stack, these two stacks become -1 shifted symplectic. So there's a special perverse sheaf living on them, locally constructed as a vanishing cycles sheaf. And that gives rise to the so-called critical cohomology. So the conjecture is that critical cohomology of these two stacks should be the same. So this is conjecture, and this is due to, well, I erased their names, but Davison, Padurario, Bu, Kinjo, and myself. And this is analog of, or generalization of, Hausel-Thaddeus conjecture. And the title of this talk is Non-abelian Hodge correspondence. So one can also think about non-abelian Hodge correspondence for these loop stacks. And if we look at the non-abelian Hodge correspondence, this is also conjectural. But the other side of the non-abelian Hodge correspondence, this is like maps from S1 to the moduli space, to the moduli stack. So this moduli stack is going to become representations of the fundamental group of X, but now I also have S1. So conjecturally, this should be isomorphic to the critical cohomology of the character variety for the three-manifold S1 cross X. And so conjecturally, there's a similar thing here. So the character variety of this three-manifold for now the Lang-Lang's dual group. And so if this conjecture holds, then this two should also be isomorphic. And now you may think, okay, like S1 cross X is a three-manifold, so maybe this conjecture also holds for any three-manifold. And this was actually a conjecture of Safronov. So this is like somehow a case for this version of Hausel-Thaddeus conjecture, and is that Safronov had conjecture already that for a three-manifold closed-oriented three-manifold, we have that the critical cohomology of the character variety for G and G check should be isomorphic. So this, I mean, I don't know the topological reasons for this conjecture, but I know that this would have like important consequences in three-manifold topology and Skene model theorem, like theory. So basically, what I'm saying is another justification for adding loop stack here is that under this non-abelian Hodge correspondence, it makes this Hausel-Thaddeus conjecture agree with Safronov's conjecture that's also called like Lang-Lang's duality for three manifolds. So all these cohomologies are infinite dimensional, but in this work with Wu, Davison, Padurario, Kinjo, we proved an integrality theorem for them, they can all be built from this from this BPS cohomology. So these are finite dimensional pieces. And so a refined version of this conjecture is that each of these finite dimensional pieces are also in correspondence and they are isomorphic. Okay, that's the end of my talk. Thank you very much for your attention.
Much. There are questions? Yes.
These loop stacks of MDOL, what kind of objects do they parameterize? If you just think.
So it's just the inertia stack. It's just the inertia stack. But so I guess like in derived geometry, people call it loop stack because the derived structure is important, but it's just the inertia stack.
But how should I think about an object in that thing? If I could think about an object in that thing.
Yeah,
the Higgs bundle.
I don't think I have a good answer for like how to concretely think about an object here. Really, it's like you can think about a Higgs bundle together with an automorphism, maybe. Yeah.
So you have all these isomorphisms between the cohomologies and the motifs. Yeah. But if I understood correctly, you start saying that you suspect that the spaces themselves are not homeomorphic. You have is that a suspicion, or you really have a reason?
Yeah, I don't have a good reason. Like, probably Carlos can answer this question much better than me. Like, this skepticism is expressed in some of his papers. This is so my argument is authority. Sorry. Yeah. So I don't know. Yeah.
So you have all these isomorphisms and so on, homeomorphisms. Sorry about that. But what about computation of this, say, intersection cohomology of these spaces?
Yeah, that I don't have. Yeah, but that's a great question, and it's a great next project for sure. Yeah, as you can see, like this approach for this proof is kind of far from computational methods. So formally, it's really nice to have this isomorphism, but indeed, computations would be really interesting. Yeah.
I would also have one question. I mean, you formulated this conjecture for the Moore homology.
Yeah.
And well, the only reason is because there you have purity, or?
That's a very important reason, I would say. Yeah, so to define the perverse filtration, you need purity. And that's a deep, well, I don't know, maybe you don't really need it. You can take the image, but that's a little bit weird. So
do you have any evidence?
Evidence for this conjecture? Not really. So yes, the fact that it holds for, so there is evidence in the GLN case, of course. So in the GLN case, so the case of like coprime rank and degree is known, and k-independence conjecture would imply the degree 0 case. So there is, I mean, yeah, for me, this is really strong evidence that it holds for the coprime case.
Then let's think on this again.